Okay, so today we're going to start talking about reference frames and displacement. So reference frames, what is a reference frame? Well, any measurement of position, distance, or speed must be made with respect to a frame of reference. In other words, what's the point of view you are looking at the situation from? So for example, if you're sitting on a train and someone walks down the aisle past you, their speed is maybe a few miles an hour at the most. They're not going very fast. However, if you were to stand on the ground and watch that same person walk while you were standing outside of the train, they would look like they were moving pretty darn fast. Because not only is the person walking with the speed that they have relative to the train, we add in the speed of the train if you're watching from the ground. So I have a little applet to help us understand what's going on here. So this is a river, and there are little boats, and there's a person at the top center on the ground. And right now our reference frame is the ground. So the person's standing there. If we press start, the person is walking, right? And we see the river flowing along, we see the boats moving. But if we change our reference frame, say to the boat, now the person and the ground is moving. Before, the ground was stationary because that was our frame of reference. But now the ground is moving because we have changed our point of view from standing on the ground to standing on a boat. We can also change it to the water. When we have the point of view or the reference frame of the water, the ground is still moving to the left like it was when we were on the boat, but not as quickly. And now the boat is moving to the right relative to the river. We can also, I think I can click this, go to the ground again. So it all depends on your point of view, or in scientific terms, your frame of reference. We have a really cool video to show in class, and that will happen tomorrow. So we know what a reference frame is. It's your point of view. It's how you're observing the situation. But what is displacement? Well, it turns out the terms distance and displacement mean different things in science. In everyday speech, we could use them interchangeably, but here they are different. Displacement is how far the object is from the starting point, regardless of how it got there. So if you're climbing up a mountain and you go from the bottom to the peak, it doesn't matter if you went straight up in a straight line, or if you looped all the way around in circles, or if you zigzagged the side of the mountain, your displacement will always be the same. The distance traveled, however, is measured along the actual path. So if you're climbing a mountain from the bottom to the peak, the shortest distance would be a straight line. And the longest distance would probably be circling around the mountain all the way up. So the distance is different, but the displacement is the same because your starting point and ending point are exactly the same. So if you look at this little graph, the dashed line is the path traveled. So somebody walked from here and went and walked and then turned around and stopped right here. And that total distance is 70 meters. However, their starting point was here and their ending point was here. So their overall displacement was only 40 meters. So this brings us to the topic of scalar quantities versus vector quantities. Well, what the heck does that mean? So a scalar quantity has magnitude or size only. It doesn't matter what direction it's moving in, it only matters how big it is. So examples of scalar measurements are distance, right? It didn't matter in the previous slide that the person walked forward and then doubled back. Their distance was only the magnitude or the size of how far they had traveled. It didn't matter what direction they went in. So distance is a scalar. Speed is also a scalar. However, a vector has both magnitude and direction. So it doesn't just matter how big the number is, it matters in what direction it's moving. So examples of vector values are, well, the opposite of distance, displacement. Displacement is a vector. It totally mattered what direction you were going in, right? It's moving from start to finish in 40 meters is exactly like moving forward 70 and moving back 30. So this is exactly like moving forward 70, which is positive, and moving back 30, which is negative. So the overall displacement was 40 meters. That's what we mean by a vector, is this negative number right here. The direction does matter. Another one is velocity. Velocity and speed are not exactly the same thing. They are a measurement of how quickly something is moving or how slow something is moving, depending on your reference frame. But it does matter if you're going forward or back, whatever convention you choose for that to be. So displacement is vector. If it's moving to the right, so starting here and moving this way, it's positive. So this displacement is 10 to 30 in positive direction, so this displacement is 20 meters. However, if you're moving from right to left, displacement is negative. So this is exactly the opposite. Starting at 30 and moving to 10. This person has still moved 20 meters, but they moved in the opposite direction. They moved to the left, so this displacement is negative 20 meters. We have a little equation that we use to figure out displacement. This right here stands for displacement, delta x. And the delta is the Greek letter that we use to represent change. So when you see delta x, you literally read it in your mind as the change in x, or the displacement. X here means position. So the change in position. And in order to solve for the displacement or the change in position, you take the initial position and you subtract the final. If we apply this equation to what we did in these two graphs, you can see we get the same answer. So, change in position is equal to position 2, or the final position, which in this case is 30, minus initial position, which is 10. So our answer is 20, just like we got before. If we do it on the other side, change in position is equal to final position, which in this case is 10, and we subtract our initial position, which is 30. And here our answer is negative 20. So these graphs were really easy to look at and determine that he moved 20 meters or negative 20 meters. But you can also use this equation, and this equation is pretty important. This is the definition of displacement. So here's a little applet, again, to help us understand the difference between displacement and distance. So we have a little track here, which is the red line, and the blue ball will follow the red track. And it loops around, it goes from point A to point B. The distance that ball traveled is the length of the red curve. It doesn't matter that in the middle during the curve it started moving backwards and then forward again. Remember, distance is a scalar quantity, so direction does not matter. However, the displacement is the distance between A and B. It's the length and direction of the straight line. So overall, the ball moved from point A to point B. It's the starting point and the initial point, and the difference between those two. So if we apply our equation here, change in x equals x2 minus x1, our final position is B, and our initial position is A. So the displacement here is point B minus point A. Graphing is a really important tool for us to help us visualize the motion of an object, and we are going to use graphs up the wazoo over the next couple weeks. In the very first one, let's look at a really basic displacement versus time graph. So in this type of graph, the vertical, or y, represents displacement, and the horizontal, or the x, represents time. So we draw a y and an x-axis, and the y represents displacement, and remember, displacement is represented by a delta x. And what kind of units are we going to use here? Well, displacement is a type of length. It's a kind of distance. So we are going to measure it in meters. And our x is going to represent time. And what kind of units do we use for time? We use seconds. So this is the outline of a displacement versus time graph. Time is on the x, or the horizontal, and displacement is on the y, or the vertical. So let's use this graph to try and plot the movement of someone. So we have time on the bottom, measured in seconds, and we have displacement on the y, measured in meters. So let's take a look at this. A student starts at the origin and walks 6 meters away, taking a time of 3 seconds to do so. The student then stands still for 2 seconds and walks back toward the origin a distance of 3 meters in the next 5 seconds. What will this look like? Well, let's give us some tick marks here. And here, each tick mark will represent 1 meter. 1, 2, 3, 4, 5, 6, 7, 8. 1 all the way to 8. 1, 2, 3, 4. And let's do time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15, 1, 10, right here. 5. Okay. So now, the blue is going to represent the movement of this person. And let's break it down into sections. So the very first section says, a student starts at the origin and walks 6 meters away, taking a time of 3 seconds to do so. This one sentence has 3 important pieces of information. The very first one is the student starts at the origin. So that means they start right here at 0, 0. The second piece of information is that the student walks 6 meters away. So the student will end up 1, 2, 3, 4, 5, 6, this height away. However, it took 3 seconds for that student to get there. So we count on the seconds, 1, 2, 3. And we find the meeting point of these two, which is right there. And we always want to connect the dots. So the student starts at the origin and moves up 6 meters in over 3 seconds. The line shouldn't be curved, it should be straight, but that is basically what the first leg of this student's journey looks like. Okay, now that we are at this point, we can go to the second part of the journey. The student then stands still for 2 seconds. Okay, so that means 2 seconds elapsed, so we've gone from 3 here to 5 seconds. But what was the displacement? displacement is 0. If they stand still, they are not moving and displacement is 0. So that means the next point is still at 6 meters, but 5 seconds, because time has elapsed. Okay, next part. Then they walk back toward the origin a distance of 3 meters in the next 5 seconds. All right, well, let's think about this. Initially, when you read that, you think, oh, back toward the origin, we want to go back this way. But remember, the x-axis is time. And if you move back to the left, you're going backwards in time. That is literally what that line represents. And we can't have that because none of us are Marty McFly. So what we need to do is time continues to move forward. And time has moved forward 5 seconds. So we move from 5 to 10. 6, 7, 8, 9, 10. So we are now here at 10 seconds. But the student has moved back 3 meters. So if we start here at 6 meters and move back 3, where do we end up? The displacement is -3 meters, so we end up back at 3. So the final point is at 10 seconds and 3 meters, which is right here. And that is what this graph should look like. So just to recap, the student moves forward 6 meters in 5 seconds, stands still for 2 seconds, so displacement doesn't change, and then moves back to where they started 3 meters over 5 seconds. So don't let the word origin fool you. That does not mean the origin of the graph. It means the origin of the journey, where the person started from. And that's exactly what our graph looks like. So you're going to get a little bit of practice with this tonight. But first, after you watch these lectures, you should read both web pages, reference frames, and distance and displacement. So this is the reference frames page. It's not very long, but make sure you read this. If you want to print it out to keep it in your notes, that's great. And you should also read the distance and displacement page. Once you're done with that, answer the following questions. Number 1, true or false? A, the words distance and displacement are 2 terms for the same thing. B, speed and velocity are 2 different things. 2, Mr. Pearson starts his morning at home and walks 20 meters to his office. He walks 30 meters to the dining hall and back twice before lunchtime, during which he works in his office. What distance did he travel, and what was his total displacement? So do both of these problems and be ready to turn them in the next time I see you.